Welcome back to Season 2 of That's So Second Millennium, the Catholic Science podcast, where we look forward to the new synthesis in the new millennium between faith, philosophy, and science. Welcome to episode 81 of That's So Second Millennium. In this episode, we move on during our interview with Jonathan Lunine to talk about planetary science. Why not? And as it turns out, this is an excellent week to release this episode because during the past week, the Nobel Prize in Physics was split between James Peebles in Canada, who was awarded half the prize for theoretical discoveries about the evolution of the universe, but the other half of it was awarded to Swiss astronomers Michel Mayor and Didier Queloz, I did my best, to celebrate their finding of the first confirmed exoplanet around an ordinary star, 51 Pegasi b. Fascinating story. And as we discuss with Dr. Lunine during this episode, it's revolutionized planetary science. How could it not? Now what is it now? 25 years later almost. We actually have a large inventory, much larger than our own solar system, of extrasolar planets. It's not complete. We know that there are systematic biases. We discuss what some of those are. But nevertheless, it's incredibly exciting to have the positive evidence for the planets that we do have, and to know that there are planets of types very foreign to the ones that we know of in our own solar system. So with that, I invite you to sit back, relax, and enjoy this about 11 minutes of conversation with Jonathan Lunine about exoplanets. Next week, we'll move on to that most obvious of topics, extraterrestrial life. We'll talk about the prospects for discovering that next week.
Between the two of us, we came up with a list that's far too long for us to get through in a reasonable amount of time. But if we could sort of discuss and where we can work in a sort of what perspective this gives us on faith and our attitude about creation. But just thinking about, so I'm born in 1979, and you were born a few years before that. So and of course you're an active, you've been a working scientist, whereas, I was a graduate student. I was an undergraduate student in the 1990s before and at the time I did not realize that we had discovered extrasolar planets at all. No, wait, I'm getting Kuiper belt objects and extrasolar planets mixed up. See, this is my problem. I'm more of a mineralogist. But how has that, so give us maybe the nickel tour of the discovery of exoplanets and then how that has changed the culture of planetary science.
Sure.
For the outsider to sort of get an understanding of that.
Right. Well, the short answer is it's completely revolutionized the study of planets. And so now let me go a little bit into the detail. So the first extrasolar planets were discovered in the mid-1990s. And this was it's a fuzzy boundary because for a decade before that, there were claims of discoveries of extrasolar planets, even using the techniques that are used today, that just could not be validated or not believed. And there are actually some very interesting human interest stories about some of this and some of the people who, as it turned out, had actually discovered planets that were then rediscovered later, but the data were just not good enough to convince everyone in the field. And then even after the first really crystal clear discoveries, there were a couple of pulsar planet discoveries, pulsars around planets in the early 90s, but planets around normal stars that began in 95, 96. And there was a period of about 4 or 5 years where not everyone in the field believed these discoveries. The way that these were detected, there were alternative explanations that maybe the stars themselves were pulsating and simulating the effect that a planet would have when it's indirectly detected. So really the field was a little bit like one of these cars that you try to start in the winter and it sputters and stops, and you try to restart it. The field didn't really take off, I think, until the turn of the 21st century, by which point it was clear that these planets really existed, and then the technique that has been most successful for detecting them, the transit technique, began to take off after 2000, 2001. And of course, with the launch of the Kepler mission a decade later, thousands of planets came to be discovered, and now we know that for every star in our galaxy, there is at least one planet on average. And what this means is not only is that planet formation is a common part of star formation, but it means there are innumerable planets to study in our galaxy. And many of these planets that have been detected and for which one can do some amount of characterization, how massive are they, what's their density, that sort of thing. They're not like planets in our solar system. The planets in our solar system don't represent the complete spectrum of planet types that can be formed. We have some gaps, and the biggest gap, I think, is something called a super Earth, which would be something several times or 10 times the mass of the Earth, but still less massive than the planets Uranus and Neptune. And it would seem to be a sort of a narrow, in-between thing, but it's actually not.
That's a wide gap. I mean, how many Earth masses is Neptune? 20?
Well, 20 or 30 Earth masses. So it's a big gap, and it turns out that for bodies that are rocky and a few times the mass of the Earth, some of the geologic processes that we take for granted here aren't going to operate the same way.
No.
And if a lot of that extra mass is in the form of water, for example, so that there are deep, deep oceans, that leads to a whole other set of processes. So there really are strange new worlds out there that we don't have any experience with in our solar system, and we have to reckon with that as we try to understand their properties and also understand why in our own solar system we have the planets that we have. And so it's created a lot of interesting new avenues for research. At Cornell, we have something called the Carl Sagan Institute, which is kind of an entity that sits within astronomy but extends out across campus to biologists and geologists and so forth. And the idea of the Institute is to provide a home for people to interact and think about planets around other stars in the context of what we know of our own solar system, and come up with multidisciplinary ways of learning new things about these planets. So intellectually, it's really exhilarating right now.
Yeah, it is. And of course, there's we've positively discovered, we see the evidence these planets are out there, like you say, for ones that we don't see in our solar system. We don't have a type, a 5 Earth mass planet of any type in our solar system. We don't know what that's like from direct observation.
That's right.
But there's also, if we were to put and then there's the question of what are we seeing so far, because we're seeing the planets that the techniques we currently have allow us to see. If we were 10 light years away on a hypothetical other planet trying to observe our solar system, with the techniques we have, which ones would we see? Which planets would we see? Right.
So with the capabilities we currently have, if we were, for example, around a star that was our planetary orbit and the star was aligned with the orbit plane of the planets in our solar system, we'd be in good shape. We'd see Mercury, Venus, Earth. We'd probably pick up Mars that way as well. Jupiter's orbit is kind of so long that we might not pick up the transit. This is the transit technique where you look for the planet passing in front of the star, and it dims the light of the star briefly. And with Kepler, it's been possible to do this for planets down to the size of Mercury or the Moon.
Okay.
So if we had that favorable alignment, we'd see those planets. We might not detect Jupiter and Saturn simply because it takes them so long to move along their orbit that, we might be unlucky and our program would end before we see them transit. But also,
what is Jupiter's like 12 years and Saturn's 30 or something?
So, and then, the gold standard is you have to have at least 2 transits to validate a planet. So, you're not going to wait 24 years for that to happen.
But that's a logistical question. We have the technology, we don't have the time.
Don't have the time. Now, suppose we're around a star which doesn't have that favorable alignment, which has to be really favorable. With the current techniques that we have available, without the transits, we would not be able to detect the Earth or Venus or Mercury because they're simply too small to produce the kind of tugging and pulling on the sun that we can detect with another technique called radial velocity. And so, we might detect Jupiter, but again, Jupiter is in such a distant orbit that you'd have to have a lot of patience. And so we might miss our solar system. Let's put it that way.
Mm-hmm. What would how tight an angle would we have to have in order for the edge-on technique?
It's basically a few degrees. The probability on average, if you distribute planetary systems randomly in the sky, is that 1 out of 100 of them will show a transit of one of their planets around, and it has to be close to the stars, so that the opening angle doesn't have to be really tight. Now, the way to get around this is another technique that's been used from the ground and is hopefully going to be much more effective when WFIRST is launched in the next decade, and that's called microlensing. And in the case of microlensing, you look at the galactic bulge, which is the sort of mess of stars, the crowd of stars.
The yolk of the fried egg.
Galaxy. Right. And as stars in the foreground pass sort of randomly in front of those, they will lens the light of the background star in the bulge. And if the intervening lens star has a planet around it, you can detect the planet. And the sweet spot for that geometry would be planets sort of from the orbit of about Mars out to the orbit of perhaps Jupiter. That's where the greatest sensitivity is, given the distance scales and so forth to the galactic center. So that really would open up for us a much better understanding of the architecture of planetary systems. And it's worked from the ground. People have discovered Jupiters and Saturns in, sort of not quite at the distance of Jupiter from the sun, but sort of half that. Not five times the Earth-Sun distance, but 2.5 times. But systems that are a little bit more like our own. I mean, the tendency now is we tend to see the close-in planets, not the more distant ones. So with microlensing, in the next decade, that could complete for us the census of the architecture of planetary systems, and we'd be able to find solar systems like our own.
It will fill in a lot more of the gap,
Yes.
If you enjoyed this episode, or it made you think, please subscribe to That's So Second Millennium via Apple Podcasts, Google Play, Stitcher, Podbean, or your podcast service of choice.